let's look at functional groups. Functional groups are very important in organic chemistry because they help us to classify the compounds. They tell us how to name them, and more importantly, they tell us how they will react. A functional group is an atom or a group of atoms in an organic compound that give it its characteristic physical and chemical properties. These are things like oxygens, nitrogens, double bonds, triple bonds. Anything like that is part of a functional group. The functional group is the place in the compound where chemical reactions occur. When it's just hydrogen and carbon, there's very little reaction that occurs. But once we put in an oxygen, a nitrogen, or a double bond, then we start to see reactions occurring. The functional group for the alkene is called the double bond, and the one for the alkyne, which we already studied, is the triple bond. Many of the other ones that we're going to look at have either oxygen or nitrogen. There are other functional groups, but in this class we will focus on only the ones with oxygen or nitrogen. In the following series of lectures, we will first discover how to identify the functional group, how that will help us to classify the compound, that will help us to name the compound, and we were going to focus on naming all of the different classes of compounds for much of this unit. And then once we know the classes of compounds, we'll look at how we can predict the types of reactions that these organic chemicals will do. We'll start by finding the functional groups, looking at their structure to identify and classify the compound, and then we'll talk about naming. To begin with, I put everything into a chart so that you can see the differences between the functional groups and how we classify them based on those differences. This chart lists many of the classes of organic compounds and all of the ones that we'll be studying in this unit. First off, we'll see that the first column shows us the class of compound. Next, we see the general formula. That's what it would look like without telling you how many carbons, but it tells you the important part that helps us to classify the compound. The next column has the condensed general formula, and it's just kind of an abbreviated way to see it, and you should be able to recognize both formats. Next column, we have the functional group, and this is just emphasizing exactly where we need to look at. The parts that are bolded are the parts that are important. The next column lists the functional group name, so not just what the functional group is, but the name that is special to that functional group. It is not by class necessarily, it's looking at what you see that is the similarities between them, looking at the functional group. And the final column is how to name these compounds. It has a lot of details, and you will be provided this on the exam, so you will have this to use. You do not have to memorize it, but you do need to know how to use it. In order to classify the compounds, we sort of need to look at the general formula. It gives us an idea of what type of compound we have based upon what elements are present and how they are bonded. So we're going to start by looking at the first grouping. If you look at the first three on here, we'll see that all of those are hydrocarbons. No oxygens, no nitrogens, no elements other than carbon and hydrogen. We may in the future see some that have a halogen on them, but we'll put those as halogenated hydrocarbons. Next, we see everything below that, except for the last one, has an oxygen, and the very last one has a nitrogen. So we see a lot of oxygens and a nitrogen. So we're going to look at that very bottom one first, just because it's different, and we're going to see that that is an amine. Now looking at that middle section, we notice that everything else has oxygens. So now I want to just focus on the hydrocarbons. We already talked about them, so we're going to see that the alkane has all single bonds, alkene has at least one double bond, and the alkyne a triple bond. Now let's look at the ones with oxygen. So those with oxygen can have either one oxygen or two oxygens. Notice at the bottom we have two of them that have two oxygens. We're going to separate that from the ones with just one oxygen. As we look at the ones with two oxygens, you'll notice that one of the oxygens is single bonded. The other one is double bonded. That'll help us to remember how to separate our next grouping. Now let's look at those four that have just one oxygen. We can see that there are two different groups here. On the top two, the alcohols and ethers, you'll see that all of the carbon-oxygen bonds are single bonds. Whereas in the aldehyde and ketone, we see that there is a double bond between the carbon and the oxygen. Now we have three groups of compounds that each have two classes of compound in them. The difference between each of these is not the oxygen, but what's next door. So we're going to look at the first group, alcohols and ethers, and we see that on the oxygen we have either a hydrogen or an R group. Recall that R just means hydrocarbon chain. We see the same thing with the aldehyde and ketone. We see either an H or an R that is attached to the carbon that has a C double bond O. The H and the R cannot attach to the oxygen itself because it already has two bonds. And our final group, the carboxylic acid and the ester, we'll see that there's either a hydrogen or an R group attached to the oxygen from the ester. This is going to be attached to the oxygen with a single bond because that oxygen is in search of another bond. And that is how we classify the organic compounds using their structure. We can also write a condensed general formula. Once we know the general formula, we just take out those bonds that were drawn in explicitly and we draw it without them. So the R-O-H becomes ROH. Same thing with the ROR. What we do see a big difference in is in the aldehyde and the ketone. So when you look at the condensed general formula, it is very difficult to see that there's a C double bond O there. Recall that we always write the carbon, then the hydrogens, and then the oxygen. This is how we know for sure that this is not an alcohol, but it is a aldehyde. CHO stands for aldehyde. And we see something similar for the ketone. Because the oxygen is right after the carbon, we know that the oxygen is directly attached to that carbon. And that tells us that this is a ketone and that it does have a C double bond O. For the carboxylic acid and the ester, notice that carbon has two oxygens. It does not have any hydrogens on it, so it's RCOOH and RCOOR. The only difference is that sometimes you will see it in the more correct form, which is RCO2H or RCO2R prime. That is the correct general formula, but sometimes you'll see it as you see here with RCOOH. Next column just boldens the functional group. You may see something like this on a quiz question. This is a really good part to put in a set of flashcards where you're trying to recognize those functional groups. Any one of these, the functional group, the condensed general formula, the general formula, and even the name, can be used to classify the type of compound. In this case, you may ask the name and have to be able to draw the general formula from it. This is definitely a great place to make a flashcard set to start studying these. The next thing we have is the functional group. This is not the same as the class of compound, although they are strongly related. So a hydroxyl is the functional group that makes an alcohol. When we look at carbonyl, the functional group is the C double bond O. It could be either an aldehyde or a ketone. There is no difference in the name of the functional group. That is just the C double bond O. Then we have a functional group for the carboxylic acid. That's called a carboxyl group, and that one has the C double bond O and the OH. Notice that there is no special name for the ester. There's no special name for it at all. And then the last one is the amino group, and amino groups have nitrogen in them, and that's how we identify them. And our final column is how to name these compounds. Again, the first thing you should always do is classify them, because once I know the class of compound, I know the ending for this compound. So in the case of an alkane, the ending is ane. In the case of an alkene, the ending is ene. In the case of an alkyne, the ending is ine. So you can see that the ending is dependent upon the class of compound. Every one of these classes has a different way of being announced. Of course, if you see an ending like ene, that should also tell you that the class is an alkene. These names can be given to you, and then you may have to draw what the chemical is. In that case, notice that the prefix alk is a part of each of those names. Alk just stands for carbon chain. If it's one carbon, we'll put meth. If it's two, we'll put eth. If it's three, we'll put prop. That is throughout the system. If you see alk, it means carbon chain. So you'll notice that in this column of names, you'll notice that the endings have been bolded, except for the case of an ether where the oxy in the middle of the compound has been bolded. Those are the things that indicate the class of the compound. You may also notice that in many of these, there is a number sign in front of the group. That bolded number is telling us that you must tell me the number where that group is. As you know, whenever there's a branch, you need to say a number. But in this case, these are not branches, but the actual main group of the compound. So in the case of the alkene, I had to tell you where that double bond is. what is the first carbon that has the double bond attached? That is the number we will use. We do exactly the same thing with the alkyne. In the case of the alcohol and the alkoxyalkane, I need to tell you the number where the oxygen is attached. Notice that the alkanal does not have a number. I'll come back to explain that later on. But we'll see that the alkanone does have a number, and so I must tell you where that C double bond O is attached. So that number will tell us which one is the carbonyl carbon. Then we look at carboxylic acids and esters, and notice again that they do not have a number in front of them. That means you are not allowed to write the number of the location of the carboxyl group or the ester. And again, I will come back to that when we get to those groups. Finally, we have the primary amine, where you do have to tell me where is that amine. Notice that the amino name is at the start of the name, not in the back. Now that we've discussed this chart, I would like to show you the flow chart of how I think about these compounds and how I separate them into each of the classes. And from that, I will also show you how you can develop the general formula for some of the classes and think about what the condensed general formula and the functional group look like. And then at the very bottom, we'll put a note that has the functional group name. This is sort of like doing this chart and including the logic that I use to separate each of the classes of compounds. In order to understand how to name organic compounds and the types of reactions that they will do, the first step should always be to classify the organic compound. This is how I do it. Obviously, you know that it is an organic compound because it has hydrogen and carbon in it. So the first thing we're going to ask, is there any oxygen or nitrogen present? I'm ignoring the other elements for now because we don't have any classes in this course that identify those. They are out there, we just don't use them. With the exception of the halogen. A halogen can be attached to any of these groups and the name will stay the same, but it will say halogenated. So you will see the terms like halogenated alkane, halogenated alkene, halogenated alkyne, halogenated alcohol. All that indicates is that there's a halogen attached where one of the hydrogens should have been. So we are not going to use that as a subcategory. So again, question 1, is there any oxygen or nitrogen? If you say no, you go to the left. If you say yes, you're going to go to the right. For now, let's follow the no pathway. When we go that direction, we are going to see that we have hydrocarbons because it has only hydrogen and carbon. Within the hydrocarbons, there are basically two types. The first type is an aromatic, and the other one is called aliphatic. How do I know the difference? In this case, it's a visual. You're going to look to see if you see this benzene ring. Remember, that's the 6-carbon chain with a circle or the alternating single and double bonds in the middle. If that group is present, we have an aromatic compound. Otherwise, it's called aliphatic. I will not be asking the term aliphatic on your exam. I just want to make sure you know the terminology is out there. We're done with the aromatic compounds. We are not going to do anything more than recognition of the aromatic compounds. Now let's turn to the aliphatic compounds. For the aliphatic compounds, we have 3 choices. The first one is to look at all of the carbons and see that they have all single bonds. We call that the alkane. Then we look and see if we see a double bond. It becomes an alkene, E-N-E ending. And then the last one has at least one triple bond, and we call that an alkyne with a Y-N-E ending, as expected. You should already know the general formulas for these. The general formula for the alkane is CnH2n plus 2. For the alkene, it's CnH2n. And finally, for the alkyne, it's CnH2n minus 2. There is no way to shrink this. It's already in its condensed structural formula. And so the last step is that we can identify the functional group. For the alkane, there is no functional group. It's just all single bonds, and that means that we don't know where the reactions will occur. It has no functional group. For the alkenes, it has a double bond. That's a super important part. It identifies the class of compound, and it tells us where reactions will occur. For the alkynes, the same thing. We're going to have a triple bond. It tells us what class of compound we have and where the reactions will occur. One last notation you might want to make for this is the fact that the alkanes are saturated, and the alkenes and the alkynes are unsaturated. Now, let's head back up. So when we go up to the other side, we know it's an organic compound, And then we look to see this one has either oxygen or nitrogen. So that is our next question. Does it have oxygen or nitrogen? We're going to put the oxygen containing ones to the left, and the one that has nitrogen will go to the right. In reality, there is a second common organic compound that has nitrogen, but for this unit of this class, we will only be using the amine as a nitrogen-containing compound. We do not see the other one, which is called an amide. You will need to see that in Unit 5, but for now, we're just going to say if it has a nitrogen, it's an amine compound. To draw out the general formula for an amine, we see that we have a carbon that has a nitrogen attached to it, and we'll see that that carbon chain is going to be labeled R. The nitrogen should have a total of 3 bonds, so we're going to put the other 2 bonds as hydrogen. Our general formula is RNH2. The class of compound is called an amine. The functional group has the name amino group. Now, let's focus on the 6 classes of compounds that contain oxygen. As we look at this, we know that they have either 1 or 2 oxygens. And that is our next question. How many oxygens does it have? 1 oxygen, we're going to go to the left. 2 oxygens, we're going to head towards the right. I'm going to focus on the one with 2 oxygens because it's easier to split up just the 2. We need to look closely at the structures to see how they are similar and how they are different. For these 2 compounds, the carboxylic acid and the ester, we see that there is an R group, then there's a carbon that has a double bond to an oxygen, and a single bond to another oxygen. Those 2 are exactly the same. So far that part of our general formula will be R, C double bond O, single bond O. We see that for both of them. So where are they different? In one case, we see a hydrogen attached to that oxygen that was single bonded, and in the other case, we see a R group, again, a hydrocarbon chain, attached to the oxygen that was single bonded. That means my final question here is, does it have hydrogen attached, or does it have an R group attached? So now I can draw the structural formula as R, carbon, double bonded to oxygen, and single bonded to oxygen with an H, or R, carbon, double bonded to oxygen, single bonded to oxygen, and an R group on it. Those are our 2 general formulas. We can condense that down so that the 2 O's come together and we get RCO2H or RCO2R. Next, we'll list the name of the functional group, and that is a carboxyl group. There is no functional group for the ester. Now, let's look at the 4 compounds that have just 1 oxygen bonded to them. The first 2, our alcohol and our ether, have only a single bond between the carbon and the oxygen. The second 2, the aldehyde and the ketone, have a carbon-oxygen double bond. And that indicates our next question. How is the carbon and oxygen bonded? If it's single bonded, we're going to put it to the left. If it's double bonded, we're going to go to the right. Now we can start to write the general formula. In the case of the alcohol, there's a carbon bonded to an oxygen, bonded to a hydrogen. There's nothing special about that carbon. We're going to replace it with an R group, and our general formula becomes ROH. We see the same thing with the ether. We have a carbon on either side of the oxygen. They don't have any double bonds on them, so we're going to replace those with R groups. They're just hydrocarbon chains. So in this case, it will become ROR. That is your ether. Making that into a condensed structural formula, we end up with getting rid of the bond between the carbon and the oxygen, and the alcohol becomes ROH, and the ether becomes ROR. Only one of these has a functional group name, and that is the alcohol. When you look at it, it should look similar to a hydroxide ion, OH-, but this does not have a negative charge. It is attached to the main chain, so it becomes hydroxyl with a YL. There is no functional group name for the ether. Finally, let's look at our aldehyde and ketone. For the general formula, you can see that you have a C double bond O. We're going to put R on the other side of that. We are not changing that carbon itself into an R because it does have a double bond to the oxygen. so we must show it. Then what we're going to see is the difference between the aldehyde and the ketone is whether it has a hydrogen or an R group, another hydrocarbon chain. If there's a hydrogen attached to the carbonyl carbon, that one will be called an aldehyde. If there's an R group, we have an R group on both sides, that will be called a ketone. Notice that the side that the hydrogen is on doesn't matter. So in the drawings, it doesn't matter if it's to the left or the right, but that there is a hydrogen attached to that carbon with the double bond. That tells us it's an aldehyde. If there's a R group, a hydrocarbon chain, on both sides, it is a ketone. So to write the general formula, we'll have R, which is attached to a carbon that has a double bond O, and it'll have a hydrogen on one side for the aldehyde, and on the ketone, it will be R attached to the C that has a double bond O with an R on the other side. Notice that I did use R prime. The prime just indicates that it could be the same hydrocarbon chain or possibly two different hydrocarbon chains. So it could be both of them are one carbon on each side, or it could be one carbon on one side, three carbons on the other side. Now let's convert these into their condensed structural formula. Recall that when we write the condensed structural formula, we start with the carbons. In this case, we're going to start with R, which is just the carbon chain, assuming how many hydrogens are there as needed. So we'll have the carbon chain. Then we're going to have the carbon with the oxygen attached to it. If there's a hydrogen, we list that hydrogen and then the oxygen, as we see in the aldehyde. It becomes R, C, H, O, indicating that the oxygen is attached to that carbon. For the ketone, we have an R group, then we have the C double bond O, and there are no hydrogens. So it becomes R, CO, and then the additional R group as the hydrocarbon chain continues on, so that the condensed general formula becomes RCOR. Because all of the reactions that happen with aldehydes and ketones really focus upon that C double bond O, they both share the same name for their functional group, and that is carbonyl. Sometimes I'm asked, how do I know what the name of the classes are? For the first three, most people have that, the alkane, the alkene, the alkyne, because we've learned that already and they're a little bit different from the others. But the other ones, when we get to the alcohol, the ether, the aldehyde, the ketone, the carboxylic acid, the ester, the amine, there's no real consistency between them. So one of the things that I do is I just do a mnemonic. This is nothing official, just something that helps for me. And I look at it and I say, okay, in each of those groupings, I have something that starts with an A and something that doesn't. Maybe you don't quite see it in the carboxylic acid ester one, but we'll get back to that. So what I found is the one with the hydrogen is going to be the alcohol, the aldehyde, the acid of the carboxylic acid, and the amine. All of those start with A. Then the ones that are not that, the ones that have an R group on them, are the ether, the ketone, and the ester. For me, that helps just to remember which one's which. Again, the carboxylic acid is a little tricky because if you think of it as acid, then you'll get it right. I hope that helps you to identify the functional groups and to classify the compounds. In the end, the best thing to do is to practice. The more you see them, the more you practice it, the better you will get. Good luck.